Great. Hi, everyone, both in the room and on the Zoom. Um, I'm Rebecca Wright, Director of Computer Science at Barnard, and I'm here to welcome you to our computer science seminar. Particularly pleased to have with us today Thomas Koch, who is a final year. He doesn't say how many that is. Electrical engineering PhD candidate at Columbia University, studying in the Systems and Networking Lab with Ethan Katz-Bassett. He received his bachelor's and master's degrees in electrical engineering at Cooper Union and is interested in how large networked applications that we use every day are delivered on the internet and what we can do to improve performance. Also interested in developing measurements methods that indirectly infer properties of the internet. And he will be talking to us today about that work.
Thank you. Okay, hello everyone. Let's get started. So are any of you ever amazed by the little rectangle in your hand that can seamlessly back up those really important photos that you took last year, or supply you with endless Netflix episodes in about a second, or let you video chat with anyone, anywhere in the world? In other words, are any of you curious about how the internet works? Well, today we're going to look at some of my work on the internet, and specifically internet routing, which asks the question, how does information get from point A to point B? Or how does a picture of your face get to your friend's phone? And specifically, I'll talk about what applications a popular method of internet routing supports and how I've helped improve routing for next generation applications. But before we get into that, first, just a little bit about me. I'm Tom. It's nice to meet you all. I'm wrapping up my PhD at Columbia, and I'm passionate about CS teaching and internet research. And both of those passions are combined in this photo I'm showing on the slides. It's a hackathon I run in my undergraduate networking class, where the students are building their own class internet. And at the end, they have a working functioning internet. But I'll talk more about that a little later in the talk. And today, I'm going to give you a brief overview of internet research in general, because we might not all know what there is going on in internet research. And then I'll give everyone a little internet crash course, just so we can all be on the same page when it comes to my research. And I'll talk about the research I've done and the research I plan to bring to Barnard. So let's get into it. The internet, first of all, what is the internet? It's many things. But first and foremost, it's an interconnection of tens of thousands of organizations, all connecting to each other in a complex graph. It's also perhaps the most inspiring way you can describe the internet. It is the most complex and dynamic system that humans have created. And so I think it's inherently worth studying. Much maybe less inspiring on a lower level, it's a bunch of protocols, algorithms, and best practices that enable the technology of the internet. Physically, it consists of end systems. So things like your cell phone, servers, devices like your smart fridge, all of those things comprise the internet. Physical infrastructure, also that you might have not seen, like millions of miles of fiber optic cables spanning the globe, satellites, increasingly Elon Musk is sending more and more, data centers and routers. So shown here is someone laying a fiber optic cable onto the ocean floor. It's going to enable high-speed connectivity between land masses. And here's a typical picture of a data center. You have rows and rows and rows of thousands of servers waiting to answer your queries. But today I'm going to talk about the internet mostly as an enabler of transformative applications, which is how a lot of us know the internet today. And we know that the internet enables great applications, but it's important to remember that it couldn't always do that. For example, if you had the average speed of a user in the 90s, it would have taken you a whole day to download a Netflix video with that slow connection. So applications that we take for granted today wouldn't have even been possible or thinkable in the 90s. So sitting here thinking that the internet works great, let's ask, well, what more could it do? And there's still room to improve. The internet's not reliable enough for telesurgery or fast enough for VR. And there's emerging applications for which we're questionably there. Like here is a 5G enabled warehouse with robots using the network intensively to make complex decisions, or autonomous vehicles making critical decisions based on the network. Thinking more bigger picture, sitting in the 90s, could you have imagined Netflix? So also let's think what as yet unthought of applications could a better internet support? These are some of the reasons why we want to do internet research. And so that brings up my topic in internet research, but there's lots of other topics. So I'm focusing on these emerging applications and how we can support them. But there's lots of other interesting topics, and internet research is an active area. Net neutrality, equitable access, all great areas with interesting questions to answer. But ubiquitous in all of these areas are a few key challenges. And first and foremost is that the internet is distributed and therefore information hiding. If I want to go and know a property of a network, say, I can't just go and ask every network in the world because there are tens of thousands of them. So that doesn't really scale. And also, it turns out that a lot of these networks are global distributed entities themselves. And so they might not even know the answer. Or they just might not want to tell you because it's a trade secret. Another key challenge in the internet is getting things to change. Let's say that you have a great new idea for how a protocol should work to improve the way something on the internet works. Well, I can't just go and change everyone's phone or all the routers in the internet, how they're working. So it takes time for things to roll out. Things need to be incrementally deployable, provide immediate benefit. And so that kind of limits or constrains these types of solutions that you can create. Related to this point is that solutions are hard to test. It's hard to get your idea out there and see how it actually works in the real world. A unique thing to internet research is that we can't really simulate a lot of what goes on in the internet. And that ties back to this first point. No one can really measure the internet well enough to simulate it convincingly in a lot of problems. And so it can be hard to really test your solutions convincingly. And with my internet research, and specifically, I'm looking at emerging applications, there's another challenge that I'll talk about. But for emerging applications, it turns out that a lot of the key players who are offering these things are a small set of large service providers. And these are the names that we know. Maybe we don't love them, but we know them. They're the Googles, the Metas, the Akamais of the world. They're the key, they're on the forefront of bringing these emerging applications to us. And so when it comes to solving networking challenges for emerging applications, what that often means is actually asking ourselves, what interesting networking challenges do these players face, and how can I solve those? And so a challenge for me as a researcher is, well, I'm not one of these large service providers. So how do I know the challenges that they're facing? And how do I go and test solutions to those challenges? Well, to overcome these challenges, I've adopted the following approach to conducting my research. And it starts with this process. And I'll talk about this process more today. But it starts with the applications and asking, what do these applications require of the network? What are their performance and reliability requirements, for example? And then based on those requirements, then it goes and informs how you should modify the network. In other words, I iterate on the network based on the application needs. I've also used a lot of tools in my research process, and these come up again and again, and they come up in interesting ways in internet research. So not just me, but others in internet research often use these tools. Collaborations, internet measurements, and global testbeds and platforms. And I'll talk about all of this as we go through the talk. Well, that's an overview of internet research and my research on a very high level. But before I go any further into my research, I want to give everyone a little crash course on the internet. So I'm sorry if this is a review for some of you, but just to make sure we're all on the same page. And let's start with just defining what a network is. A network is a group of end systems. So think of your phone or your smart fridge or a bunch of servers at a data center, and they're all communicating with each other and managed by a single company. I'm going to use this icon, this like computer icon, to indicate something more user-centric, like a computer, a phone. And then I'm going to use this icon over here to represent something like a server that lives in a data center. So one type of network is an end user network. And these are names that we're probably pretty familiar with. They're the companies like Verizon, or Columbia has a network, or Spectrum. These are networks that work on usually a subscription model, so offering users a service for some money. On the other hand, there are networks without any users, and these are the service provider networks. They're just there to provide a service. A third network that maybe we haven't heard too much about is a core network or an infrastructural network. And their key purpose is to connect the networks together to enable connectivity between all the networks on the internet. And all these networks are connected to each other in a huge graph. And that's what comprises the internet, basically. The internet is just a network of networks. Now, a key performance metric of interest for me is internet delay or latency, and specifically a type of delay or latency that's really pertinent to my research area. So I'll talk about what that is. So internet applications are all about getting information from point A to point B. So for example, between these two networks. And on the internet, we basically send light pulses on wires to do so. Since light is lightweight and it's fast, it's really fast, it moves at the speed of light. But light still takes some time to travel. It takes about 200 kilometers per millisecond on the internet. And you don't really need to know that number exactly for the purposes of this talk, but that's just to kind of put into perspective. It would take about a half a second to get from here to Australia and back. And in internet applications, we have to do that several times. And so these delays can really add up and become significant. We call this type of delay propagation delay because it's the delay that light is literally propagating on the wire. And it's the type of delay on the internet that I'm going to be talking about the most today. And propagation delay can really affect your quality of experience. So let's say that two users in these networks are having a voice call. Their propagation delay is small, so they're having a good quality of experience. But take the same application, same networks, and just increase the propagation delay, and that experience might turn negative. I'm sure we've all had that experience on a phone call where we're both silent for a second, and then you both speak at the same time and you interrupt each other. It's really annoying. It ruins the voice call. And you can just abstract that negative experience to other applications, like when you're browsing the web, or you're playing a game, or new ones like VR. High propagation delay hurts experience. And it's kind of hard to put like exact numbers on what's high and what's low or good and bad. But generally, good propagation delay would be about 30 milliseconds. So we measure delays in milliseconds or hundreds of a second on the internet. And bad would be like roughly more than 100 milliseconds. But that can vary depending on the application. Now, my research looks mostly at interdomain routing. And interdomain routing answers the question, how should information get from organization A to organization B on the internet? Like how should a video in B's network get to A or vice versa? And so if A is trying to access a service on B's servers, what B basically says is, hey, internet, you can find me at this address, 1.2.3.4. And that's an IP address. So I know we've all seen IP addresses, but this is basically what they're used for. It's to enable routing or how to get from point A to point B on the internet. And so what happens with this address advertisement is B goes and announces this to a connected network next to it. Information about where B can be reached then propagates through the internet. Each network passes information about where this address can be found to the next in this kind of propagating way. So each network is making its own decision about how to pass that information on. Now, by backtracing how that information propagates through the internet, you spell out an interdomain path or route through the internet between two networks. Now, the interesting thing about interdomain routing is that by advertising different addresses in different ways to connected networks, we can spell out different paths between the same two endpoints. So if I take another address, 5678 from B, but I instead advertise it to this network down here instead of that one up there, information about where this address can be found now propagates differently through the internet. So taking this bottom path instead. Similarly, by backtracing how this information propagates, we spell out a path through the internet between the two endpoints. So same two endpoints, different interdomain path. Why might we want to do that? Well, first, two paths is better than one. One fails and you have a backup, so that's good. But also, these paths might be of different physical lengths, and therefore they might have different delays or propagation delays. So this top path might be a little longer and have 150 milliseconds of propagation delay, whereas this bottom path is 50 milliseconds. And so you kind of come across this interesting problem where maybe you can find the best path between A and B in this interdomain sense. You can set up a sort of optimization problem. But it's a challenging thing to optimize these interdomain paths. And there are a few key challenges. The first of which, we don't know what this graph looks like. We have imperfect knowledge of the internet. So I'm putting up for us here nicely But in reality, the internet is too distributed and difficult to measure. No one can actually see this graph. Moreover, even if we could see this graph perfectly, it's difficult to predict paths through this graph because each network decides how it's going to propagate information independently of the other via a process that we have limited insight into. A third challenge is scale. So even if we could predict paths, optimizing finding the best path is challenging because B is not just connected to 2 networks, because in reality, it's more connected to like 10,000 networks. And so there's 2 to the 10,000 possible announcements to look for each pair of endpoints. So it's a really challenging problem. But just bringing us back to the beginning, this is sort of what my class was looking at. They were looking at intradomain routing. In this hackathon, they're setting up intradomain routes between each other. And at the end of it, they can actually, from a student's network, fetch things over other student networks from like a web server over here. So they build a real working internet with real interdomain routing. It's pretty cool. But that kind of concludes our internet crash course. So we're all now internet experts, or at least we have a good idea, at least of what the internet is and how things on the internet get from point A to point B. So let's apply this information and look at my work on a popular intradomain routing technique used today, and my work on a new routing technique for more next generation applications. Now, as I mentioned, these next generation applications are often served by these large service providers. And so my research looks at how these large service providers deliver their services and how they could possibly improve that. So since large service providers generally have global user bases, they have global networks that span the globe. And their goal is to bring performance service to billions of users in hundreds of thousands of networks. And so they create data centers with servers waiting for your queries to offer these services to the users. But having one set of servers is not a great idea because if that fails, then you're out of luck. And also you want servers that are close to all your users all around the world. So they often build replicas of these servers, all performing the exact same service, and they interconnect them in like a global backbone. So these are global networks. To bring these services to users, they have to connect to your network eventually. And to do that, they generally come together in large cities. So they'll come together in large cities at what are called sites. Here, they'll connect to a bunch of core networks to bring connectivity, to bring services to users all around the world. And so these tend to be in the major cities like New York City, Chicago, or all the way in Seoul. It's where the connections with other networks happen. They'll connect to different networks in each of these cities. So over here, they might connect to Spectrum, whereas over here, they might connect to Korea Telecom, say. And so a user can be routed through any of these sites, and it doesn't really matter which one they hit from a service perspective, because eventually it'll just connect to a backend server, all of which are replicas of each other. And so all of these sites essentially serve the same service. But the question that I ask in my research is, how should I advertise addresses from this global network? And a very simple answer to this question, in fact, probably the simplest answer we could think of, is to just advertise the same exact address to everyone from everywhere in the world. And this is called Anycast. It's advertising the same address from everywhere in the world to all your connected networks. You then rely on the internet's protocols to decide who gets routed where. So this user might be routed here, this user might be routed here through that interdomain routing process I talked about. So you're relying on the internet to decide who gets routed where. There's no complex decision-making on your end of you should go here, you should go here. And because of that, this can be viewed as a simple scheme. It's simple because you're offloading that decision-making to the internet, and also simple because it's a very simple idea. You're just advertising one address. It's also quite reliable, and it's reliable in the following sense. So let's say that something bad happens, like there's a power failure in this city, and that site goes down. Well, then that address will no longer be available there for people to visit. But what's great about the internet is the internet says, oh, you're trying to go to address 1234. It used to be here, but it's not there. But you're still trying to go there. So, oh, here's 1234. Eventually, it'll just route you to a different site advertising the same address. It's kind of like if you're at the grocery store in a checkout line, all of the checkout lines can perform the exact same service, and you just need to route to one of them. And because of this simplicity and built-in reliability, it's used by many large service providers. So all those big names that I had up on the slide use Anycast in their deployments today to do inter-domain routing in some way. But this simplicity comes at a cost. There's a pitfall here. So let's say that this user is visiting this site and it's in their city. So there's a low propagation delay, only about 5 milliseconds. That's pretty small from a networking perspective. But what can happen, what can go wrong is the internet can say, well, you're trying to go to 1, 2, 3, 4. So there's 1, 2, 3, 4, go there. But there can be on the other side of the world. And you're inducing this really unnecessary large high propagation delay of 150 milliseconds, hurting the user's experience. The key problem that causes this is that inter-domain routing process that I was showing you all is not performance aware. Nowhere in that process was performance taken into account, just independent decisions made in different organizations. We can quantify this inefficiency with a metric that I'm going to call latency inflation. And latency inflation is just what you're getting, 150 milliseconds, minus what you could get, 5 milliseconds. So 145 milliseconds of latency inflation here. So assessing how good this strategy of advertising addresses is, Anycast, how good is Anycast? What we really want to see is, well, how bad is latency inflation? How often does this occur? If it never occurs, it's not a problem and Anycast is fine. And the literature was split on Anycast. You had some folks saying that Anycast has surprisingly large inefficiencies, while others said, well, Anycast works pretty well. And these are different opinions, samples of many, in major conferences like SIGCOMM and IMC, which are major conferences in my field. And so I wanted to know why there was such a striking difference of opinion on this really widely used strategy. I mean, more than just the literature, we had folks that worked at large service providers coming to us and being like, yeah, apparently Anycast isn't good, but we still use it and we're not sure why. So I wanted to get to the bottom of this. And to do that, I looked at Anycast in two important systems on the internet. First, in the root domain name service. Now, you don't really need to know what the root domain name service is. You just need to know that it's critical for the internet to function. And its content rarely changes. So its records are easily cached by users and other parties. It's a huge deployment. It's spread over about 2,000 sites all around the world. And it's managed separately by 12 different organizations, all of which are doing the exact same thing. I next looked at Microsoft's content delivery network, which is Microsoft's network that delivers web content and serves web content for Microsoft and its customers. So like if you wanted to host an application or website with Microsoft, this is what you'd use. So we're talking about many applications, dynamic content, not so easily cached. It's spread across the world over about 100 sites, and it's managed by one single organization. So one thing to note here is that global optimization is possible because you just have one organization managing it. Maybe from these facts about the root domain name service, we can infer that a key goal of the root domain name service is maximum resilience. In fact, it's so resilient that even if you compromised an organization here and you took it over and took down its root domain name service, the root domain name service as a whole would still continue to function because there are 11 other organizations ready to do the exact same thing. Microsoft, on the other hand, possibly cares a little bit more about performance and flexibility than the root domain name service. But anyway, I went and looked at that metric, latency inflation, in both of these systems. And that's what I'm showing here. On the x-axis, I'm showing latency inflation measured in milliseconds. And on the y-axis, I'm showing a CDF of users all around the world. And so a way to read this point right here is that 0.5 or 50% of users experience more than 50 milliseconds of latency inflation. That's what those red dots. The red dots here are showing the root domain name service. The blue X's are showing Microsoft. And so immediately we're seeing there's lots of inflation in the root domain name service. More than half of the users are being inflated by more than 50 milliseconds, which is quite a lot. On the other hand, for Microsoft, inflation is comparatively small, almost an order of magnitude difference in the 80th percentile. So then I wanted to ask the question, well, how does this inefficiency affect users? Because if it doesn't affect users, it's not a problem. And so what I did is I went and quantified the number of times per day on average that a user would interact with the root domain name service. And that's what I'm showing on this graph. On the x-axis, I'm showing queries per day that you would send to the root domain name service. And on the y-axis, I'm showing a CDF of users globally. So this point right here in the middle means that half of users send less than one query per day to the root domain name service on average, which is, hopefully we can agree, not very often. So you're experiencing 50 milliseconds of latency inflation, but on average, less than once per day. It's nothing. And this happens because of caching. The root domain name services records are very easily cached, and so you rarely actually need to interact with the service. In other words, performance doesn't matter nearly as much in the root domain name service, whereas it matters a lot for Microsoft. To load a single web page, you need to interact with Microsoft's network several times. No such caching there. And because of this performance requirement, Microsoft works hard to prevent inflation. And so its Anycast strategy works better. So some high-level takeaways from studying Anycast performance, and this can kind of be brought to other areas of computer science as well, is that you have to keep context in mind when you're assessing the utility of a technique. And one strategy that you can use here is to analyze a technique in multiple contexts to really tease out how it affects overall system performance. Specific to Anycast, I found that Anycast is performant enough for some applications, and it can get better with more incentives and operator effort. So analyzing in one place does not necessarily translate to another. From an enabling applications perspective, Anycast is really flexible. It can be performant and it can be reliable. So if we're looking at the reliability and performance requirements of a given application, Anycast can really run the gamut of what it can give you. It can give you high performance with low reliability requirements, or really high reliability requirements and low performance requirements. I presented this at SIGCOMM in 2021. Okay, so this is a good time to talk about some of the strategies that I used to get this research going. And it's a really common thing that I engage in and that a lot of other internet researchers engage in, as well as working with collaborators to solve interesting problems. Part of what makes internet research hard, what I mentioned, is that it's hard to get your hands on real data and to see what the real problems are and to answer interesting questions. But by collaborating with industry leaders, it gives you insights into real problems and data. So I worked with DNSORG, which is like a critical internet infrastructure company, and Microsoft in this study to answer these interesting questions. And I'm looking forward to interesting Barnard undergraduates to these opportunities because they often lead to internships, jobs, positions in academia, et cetera. Another tool I used, and I'm going to use in the following study as well, is measurement platforms, which are ubiquitous in internet researchers. As I've intimated, we need help to answer questions and test systems because simulating the internet is often just too hard. So one tool that a lot of us use is publicly available measurement platforms. These platforms are often free to use. They might be research projects in of themselves, and they're collaborative and community-driven. And I see these platforms as like this democratizing force in internet research that allows everyone, even me, to conduct groundbreaking internet research, conducting experiments at global scale. And so what might one of these look like? Well, this is Ripe Atlas. It's this web interface where anyone can go and conduct measurements on the internet. So you can go and create a measurement. Maybe you want to make it a latency measurement or a ping measurement. And you can select probes from all around the world from which to make this measurement, talking thousands of networks in hundreds of countries. So it's pretty cool. And I see measurements as a great way to get undergrads involved as well, because they're interacting with the actual internet, and they're having like this tactile feel of the research problem they're working on, which I found very valuable when I was first working in this field. As part of my dissertation, I actually helped enhance a current platform on the internet, which introduces a lot of new opportunities. This platform allows you to conduct real-world routing experiments as if you were a global service provider with realistic connectivity. So we're talking 10,000 connections to other networks at 30 sites all around the world. Here's kind of a global view of what that looks like, which allows you to go into the internet, advertise your own addresses, and see how the internet reacts to your experiments in real time and measure performance from other networks. When I was interning at Microsoft, they wouldn't even let me do that. If I said, oh, I want to advertise an address from your network, they'd be like, ha, good luck. So this is a really great opportunity, and it enables new research directions, like routing optimization. And so I'm going to show you how I use this platform to enable a new idea that I'm going to talk about next. So stepping back a second, I looked at Anycast and the applications it was supporting, and I basically found that, well, there was really no iteration needed. The network was providing what it needed for those applications, whether it be web browsing or critical internet infrastructure. But a question is, when the application becomes more critical and with more performance requirements than you think Anycast can provide, can Anycast still do the trick? And these are a lot of the emerging applications and use cases that we're seeing today. And the short answer is no. Things like the inefficiency of Anycast in the tail especially become unacceptable for these emerging applications and use cases. And I'm going to build a specific use case that maybe we can relate to in our day-to-day lives. And it has to do with enterprise use cases on the internet. So 5 to 10 years ago, let me paint a picture. A lot of critical enterprise services like student schedules or sales databases or email, those were all hosted locally on the local business's network. And that was a really simple way of going about things, but it was also inefficient. It was expensive to upgrade. And so increasingly what enterprises are moving to is a model where they access critical services in, say, the cloud, where there's more reliance on intensive network usage. So as an example, robots in a factory might access a machine learning model in the cloud where there's more flexible resources and use cases. And so this is a really flexible approach and it's efficient, but it also means something new, which is that if you have bad connectivity, that means you can't do your work well. These critical use cases, you're running into problems. So imagine a robot's trying to make a decision about what it should do next, and all of a sudden the connection slows down. That's a real problem. And so clouds ask the question, how could they better ensure reliable, performant connectivity for these sorts of critical use cases? And I went and solved this problem by building a system that I called Painter. And Painter kind of starts with, well, first ditching Anycast. Anycast just won't do, it's not performant enough. And my motivating use case here is you kind of have this bunch of enterprises, and maybe the enterprises have robots that are interacting with the cloud to make decisions, evaluate machine learning models, that sort of thing. So the first component of my system, Painter, went and computed better address advertisements from the cloud. So it uses a combination of machine learning, internet measurement, and internet modeling and optimization to compute the best addresses to advertise. And so the output of my path or address optimizer is a set of addresses to advertise from different sites around the world. And so you might have many addresses being advertised instead of just one, and they might be advertised in different ways in different areas. You also might have different addresses advertised to different individual networks. And so this is a really challenging optimization problem because of such a large space, and it's difficult to model what you're optimizing over. But at the end of the day, for example, this enterprise down here will now have a set of available paths that it can take to the network, improving reliability, perhaps performance. The second component of my system involves placing a powerful network device in enterprise networks that I'm going to call a traffic director. Now, normally, you can't do this when you're creating a networked solution. Like if I wanted to improve the way that your phone works, I can't just go and modify how your phone works or place a powerful network device in your home. But this sort of enterprise cloud setting represents a setting where enterprises really need their robots to work, and clouds really want to work with enterprises to make them work. And so it's like a unique place where we can be a little more flexible with how we're solving a problem. The traffic director's job is to measure these paths and place traffic on them dynamically at really fine timescales. And so Painter, this system, is the combination of this intelligent address advertisement from the cloud and this fine-grained traffic direction and measurement from the enterprise's network side. So I'm going to show you a little demo of sorts on that test bed that I talked about. So I went and advertised real addresses in the internet and measured real performance. And so what I'm going to show you is how Painter can improve performance and availability from the perspective of a single enterprise network. But these are like real experiments, real routes on the internet. So this graph is going to be a latency time series for that given enterprise's network. So Painter's path and address optimizer goes and computes the best addresses to advertise from its network. And so here it's choosing, okay, I need to advertise a red one from over here and a blue one at this site and some brown ones over here. And I'm also going to advertise an Anycast address just to show for comparison. So each of those bubbles is a different address being advertised. And that's all pre-computed. It only needs to occur like once a month or so. The traffic director in the enterprise's network measures performance on each of these paths. So that's what's being reported in this graph right here, the latencies along each of those paths over time. And it sees that this red path is the best path to place traffic on. And so that's the path it chooses. But then what I did at a certain point is I simulated a site failure. So the site that this traffic director was visiting fails, and those addresses no longer became available. Well, remember I said that Anycast is reliable. It eventually reroutes the client to a different site. Well, here that occurs after about a second of complete unavailability and 30 seconds of network instability, which isn't great given that these are really critical applications running in possibly tens of thousands of networks. Painter, and the traffic director on the other hand, instantly detects this failure and shifts traffic to the next best path, the backup blue path. So it's providing maximum performance and availability. So some key takeaways from looking at Painter. First and foremost, Anycast is good enough for traditional applications like fetching web content. But the next generation of applications require stricter guarantees, these sort of emerging use cases. And that's where Painter can come into the picture. It brings us towards providing those guarantees for a wide array of applications. And because of that, it's in discussions to be deployed at Microsoft. I also presented this at SIGCOMM this year. So that's a little bit about the routing work I've done, the research that I've done. Let me talk to you about what I'd like to bring to Barnard. And on a high level, it involves moving beyond routing, but with the same approach and the same high-level goal of enabling next-generation applications, but extending my approach along all legs of the hypothetical path. So I'm talking all legs of the path from the user's phone to their ISP, into the network core, and even more problems to solve in the service provider's network. For example, some questions I'm interested in answering are, how can application developers better interface with low-level network primitives in this era of new application requirements? Or can we use advances in computational hardware to change the way that we're switching traffic in the internet? Or can I use ideas like the ones I presented today to mitigate things like DDoS attacks? But I'm also interested in other questions and the interplay of routing with other areas of internet research. So internet routing, having multiple routes and putting traffic on each of them and choosing that has implications in economics and governments because it gives you more control over where your traffic's going. So there's like interesting interplays to think about there. And I see internet research as great for working with Barnard undergraduates. There's lots of great opportunities for undergrads. And I think internet research is a particular area of computer science research that's particularly amenable to them. And partially because of the tools that you use all the time in conducting internet research. Undergraduates can work with internet measurements. It's giving them a tactile feel of the problems they're working on, and it allows for iterative growth and understanding of the way the internet works. Collaborations introduce them to opportunities for jobs or internships or academia, and you can access global testbeds and platforms even if you don't have many resources as an undergraduate. But more than anything, working on the internet is just fun because you're working on important applications or relevant applications in your life. Part of what keeps me interested in internet research. And I've had lots of great experiences working with mentees, both graduate and undergraduate, some of which had no background in computer networks and some of which went on to do PhDs in the subject. So I think they had a good experience. But just to give you a sense of like a sample starter project or problem that I think many undergraduates would find interesting, involves encryption. So a lot of us, when we're accessing the web, our data is usually encrypted. Like if you're typing in a password, I can't just look at the network and say, oh, that's your password, because it's encrypted. But some information about what you're doing still leaks to the network. And so the project would kind of involve unencrypting that. So if I look at the traffic, the encrypted traffic traversing a network, can I build a model that sort of unencrypts the traffic? In other words, to what extent can I characterize what's going on in the network despite the encryption? What information is still being leaked? And what defenses can I create, or alternative ways of doing encryption or traffic traversal on the internet to prevent this sort of information leakage? And so students would gain experience here in network measurement, data analysis, and iterative algorithmic development, but no, major prerequisites. But anyway, I think I've talked too much. So summing up, hopefully I've convinced you that internet research is active and it's fun. And I've talked a little bit about how I've helped pave the way towards providing next generation networked applications. But there's a lot more that I didn't have time to discuss today. So I'd be glad to talk to you about that. And I've shown you a little bit of my vibrant research agenda that I'd love to bring to Barnard. So at this point, happy to take questions.
Thank you, Tom.